All right, so in this video, we are going to talk about clustering, right? This is on the unsupervised topic, basically. So in this course, we've spent a lot of time looking at supervised learning, machine learning algorithms, and that's very important. But a lot of cybersecurity professionals will usually tell you that whenever they implement machine learning tools, they do a combination of both supervised and unsupervised. So there might be some tasks where unsupervised learning is more useful. So in this video, we will discuss unsupervised learning, some unsupervised learning techniques. So when I say unsupervised, I basically mean that there's no labels. All right, so that's really the idea. So we won't be doing classification per se, but there's a few techniques that we can still use without labels. All right, so we will look at specifically two techniques. One is singular value decomposition. And singular value decomposition is like principal component analysis. So it's a technique that allows you to take, let's say, a vector space of maybe 1,000 features or 100 features or 30 features, and you're going to compress them into a space of just 1 or 2 or 3 features. All right, so that's really the goal of this. I'm not really going to go into too much theory on this topic. Instead, we're just going to do this in sklearn and kind of get a feel for how this works. So I'm also going to create data like raw data on my own with the code, and then we will analyze it. So after we cover singular value decomposition, we are going to look at clustering, and in particular, we are going to look at the k-means clustering algorithm. All right, so it should be pretty straightforward. We're going to create a data set and hopefully plot our information and see how these algorithms work. All right, so since we're using sklearn, so I'm right here on the desktop right now, and I'm going to create a new script. I'm just going to call it, unsupervised, let's say. So I'm going to do this lowercase unsupervised.py. Right, so this is pretty simple, simple script. And then I'm going to import in here the sklearn language, right? So the module sklearn. I'm also going to import singular value decomposition. So sklearn from sklearn.decomposition. So decomposition. I'm going to import truncated SVD. So truncated SVD is the version of SVD. It's a little bit of the math that makes it truncated SVD, but as I said, I don't want to get into the math of singular value decomposition. It involves a little bit of linear algebra concepts, and so we're just going to use it as a tool. If time permits later on, I may create a video on the theory of it, but as I said, I think with the example it'll become obvious what I'm doing with the data and hopefully the usefulness of singular value decomposition. All right, I'm also going to use a tool that we already use in the malware lab, or the fileless malware lab, where we use count vectorizer. So I'm going to use that again. So if you remember, count vectorizer allows you to take documents with a lot of words or files with a lot of codes, and we can find the frequency of the words. So we can take a bag of words approach to solve our data set. All right, so I'm going to, from sklearn dot feature extraction, I'm going to, and feature extraction text, so dot text, I'm going to import count vectorizer. All right, count vectorizer. And I'm also going to import the k-means algorithm. So I'm going to say from sklearn.cluster, I'm going to import k-means. So the k-means algorithm. All right, so these are all the libraries that I'm going to import here. All right, if you're following along, this code should be on the GitHub repository as well, so if you want to get it from there. Oh, I'm also going to use pandas here, so I'm going to do import pandas as PD. All right, and import numpy as NP. All right, so that's the libraries. Let me save this so I don't lose it. And also, I'm going to run these, make sure I have the libraries available. All right, so the libraries are there. All right, so now I'm going to go ahead and create some data. So in this case, I'm just going to take a very simple example for singular value decomposition. I'm going to do some sentences. Oops. So I'm just going to say cybersecurity. Oops. Cybersecurity is super fun. Super fun, and then I'm going to add a comma here. Oops. And then I'm going to say TensorFlow is super, comma, super cool. And then, statistics is cool too. And I'm intentionally adding words in here that, because I want some words to occur in multiple sentences. Okay, so statistics is cool too. And then we're going to say machine learning is fun. Python is great for machine learning. Python is great for machine learning. And then, so if you notice, all of those sentences were of a specific topic. All right, and we can actually give this a theme of like more cybersecurity. So I can say cybersecurity is cool too. Right, and then machine learning is fun for cyber security. Okay, and finally, Python is great for machine learning. And all of those sentences either relate. We as people would say that these relate to either. We as people would say that these 5 sentences relate to either cybersecurity or machine learning data science. All right, and then I'm going to add another set of sentences, 2 more, and I'm going to say I like, let's say a sport, so karate. I like karate. All right, and then finally, one last sentence, we'll say soccer say soccer is great to watch. All right, so if you notice, these last two sentences really don't relate at all to machine learning or data science or cybersecurity. Instead, they relate to sports, but you're talking about things that you think are great or fun, etc. So you say, for instance, soccer is great here, and then you also say Python is great. So that word is common to a sentence from the data science group and then to a sentence from the sports group. Okay. All right. So now this very simple data set is what we're going to analyze. So if you notice, we have 7 sentences. 1, 2, 3, 4, 5, 6, 7 sentences. All right, and now we are going to process this data. So the first thing we're going to do is use count vectorizer. Okay, so we're going to create vectorizer, which will be count vectorizer. And again, if you don't remember what count vectorizer does, I suggest you go back to the video on malware analysis, that whole lab video, and go to the very first video that explains pretty much, the idea of bag of words approach. But in essence, what we're doing is we're going to represent these sentences, cybersecurity is super fun, as feature vectors. Feature vectors that include all the words in this vocabulary, basically, right? So all of these words are a feature in that feature vector, and for each sentence, we're just going to indicate the frequency count. So that is, how many times does each one of these words appear in the sentence. All right, so we're going to keep track of that. All right, and we'll see that when we do the example. So now that I've done count vector, so count vectorizer is the object. So I'm going to do count vectorizer. So count vectorizer. I'm going to define the number of times, the minimum number of times that a word should appear in a document. So I'm going to say min df equal 1. So every word should appear at least in one document or sentence. All right, then I'm going to remove stop words. So stop words are words that are very common so that they don't provide really any value. So for instance, like words like the, right? So those words don't really provide much meaning, and so we can take those out. And so that's what you do here by typing stop words equal English. All right, so I've created the vectorizer. Now I'm going to apply vectorizer to the example. All right, so this is my data set, right? I'm going to create then DTM, data frame, equal vectorizer dot fit underscore transform, and I'm going to apply that to the example. So I apply this to my example, and now I'm just going to print the result. So I'm just going to say, using pandas, I'm going to create a pandas data frame, pandas data frame. All right, and it takes in as input DTM dot to array, and we're going to specify that the index should be the sentences, so example, comma, and then the columns will be the features that I just created, from the bag of words approach. So it should be columns equal vectorizer dot get feature names. So let me actually move this down. So I'm going to do the backslash here. All right, so I'm going to do get feature names, open parentheses, close parentheses, and then from this I'm just going to get like 10. All right, so the top 10 most frequent or something like that. All right, so once I've defined this, we should be able to see it. So let me add a print done here so that we know that the code ran. All right, so I'm going to do Control X, Y, and now I'm going to run the code. Python unsupervised. All right, and there you go. So you can see here, it looks really nice, right? So I created a little matrix of 7 rows, right? The 7 sentences by 15 columns, right? So the top 15 words, or something like that. So here you can see, and then I'm just showing like a few of them. So that's my matrix data, and then now if you look here, so every sentence, like cybersecurity is super fun, has now been converted into a bag of words approach feature vector like this one, right? So here we can see, for instance, the word cool does not appear in the first sentence, cyber does appear, fun appears, super appears, TensorFlow does not appear, watch does not appear, and so on, right? So that's basically the idea. Another example is here for the second sentence, TensorFlow is super, super cool. We can see that the word super appears twice, TensorFlow appears once, and so on. So that's one of the easiest ways to go, if you have a whole bunch of documents, and this is exactly the approach that we took for the malware analysis lab. So we had there a whole bunch of log files, and we converted them into the feature vector representation. So now that I have this, there's other things that I can do, right? So one of the things that I can do is I can take this data set that maybe has 15 words. So if you remember, like the malware analysis lab, for instance, had, I think, 1,000 keywords. So it had 1,000 features. But maybe you have one that has 50,000 features. And so now if you have 100,000 records by 50,000 features, that becomes a really large matrix. So wouldn't it be nice if we could do something so that we could take that matrix that is 100,000 samples by 50,000 columns and map it to 100,000 samples by 2 columns. And then maybe by doing that mapping, okay, maybe we lose some information. So whereas with 50,000 features, we have 100% of the information. If we map that to a smaller space of, say, 2, maybe now we only have 85% of the information. So we lost 15% of the information, but that 85% may actually be enough for us to do good enough machine learning. So that's what this technique is about. This technique it's a compression technique. Excuse me. It's a compression technique. It's a compression technique that allows us to take, a matrix of really large size, like 100,000 by 50,000, and compress it into a smaller matrix of 100,000 by, say, 2 or 3. Whenever we have a matrix that has 2 or 3 features, it also means that we can plot it and view it, so that's a good thing. But this is very useful for whenever you have memory issues or anything else, right? So you want to compress the data. So let's go ahead and do that. So for that, I'm going to create an object. So I'm going to say, I need to go back to the code. So let me create a new object here. So I'm just going to say compressed compressed DTM, right? So that's to be consistent. And to get that value, I'm just going to apply truncated SVD. So I'm going to say truncated SVD, right, which is our library that we imported above. And I'm going to say that I want an object of just 2 features. So I'm going to basically map my 15 or so features that I have in this example, the words, into just 2. So it's really what happens there is very much like linear regression. It's a linear combination. So you take all the features, the 1,000 times a specific weight, you do a linear sum, and then the result of that becomes the new feature, the new components, if you will, like principal components. So in this case, so now we create the object, and now we're going to apply it. So I'm just going to say actually this is, let me just say compressed SVD. I'll change that name. And then here I'm going to call this one compressed DTM. So this is the actual object. So now I'm going to apply compressed SVD, and I'm going to say dot fit transform, and I'm going to apply this function to my original DTM. So this data set over here, right, what we just saw, so I'm going to apply it to that. Okay. All right, and once I apply it, then now I should have a smaller data set. So let's do that. All right, another thing we might want to do is we might want to normalize the data at this point. All right, so normalization is usually good. So let me add another library here. So this is a good point to do that. So let's do from sklearn dot preprocessing import normalizer. All right, so I'm going to apply this normalizer to the data set. So that should just be one additional line of code. And I'm just going to say compressed underscore DTM will be normalizer set copy to false dot fit transform, and we're going to apply this to compressed DTM. All right. Once we've done this, we can just go ahead and once again print the data frame. So now we're going to have both data frames, except that one will be the data frame with the original features, all the words, and the other one will be the data frame with just the compressed features. So now we print pandas.dataframe. So pandas.dataframe. And I'm going to do compressed SVD dot components. All right, so this will print out the components that we just created. So that's going to be components underscore. We're going to specify for the index this time that we want. We created 2 components, right? So there's no more notion of the words. Now we just have. Remember, it's like we took 15 words and mapped them into a space of just 2 features. So we can call them whatever we want. So let's call it component 1, and then we can do comma component 2. Right? You could call it feature 1, feature 2, whatever you want. All right, comma. Let's add a backspace, or sorry, the backslash. All right, and then we can do columns, and columns will be equal to, so columns will now be equal to the features, right? So we're going to basically plot how the features mapped here. So I'm going to do count columns equal vectorizer dot get feature names. Get feature names. All right, and there you go. So that should be enough for us to print something here. So let's go ahead and run this code. So I'm going to do Control X, Y. I'm going to run it. All right, and as you can see now, we've taken the sentences that we had originally with in the bag of words approach, and now we have mapped it to this new matrix that is size 2 by 15. So that means that all of these words have been mapped to this component, for instance, right? So that's somewhat useful. But what we really want is we want to see these sentences, right, as represented by the two feature vectors, right? So that's the next thing that we're going to do. So we can go back to the code. Right, so we can go back to the code here. And now we're going to take, so we want to represent, so we can even say here, we want each document, or sentence in this case, each sentence is now represented by two features, which are the components. All right, so that's what we're going to do in the following code section. So to do that, I can print the data frame like this. So I'm going to do pandas.dataframe, right? And then I'm going to take compress DTM underscore DTM, comma, and now the index is still going to be the sentences, right? So example. This doesn't have to be in a list. It's already a list. Example. And then the columns will now be the principal components. So columns will be, let's say, let's call it feature 1, comma, feature 2. All right, so that's how we can do this. So let's go ahead and run this code now. Okay, I'm going to do a clear here. All right, so now I'm going to, and actually let me go back to this. I don't want to print the mapping of words to features, so I'm going to comment that out. All right, and I just want to print those two. So if I run the code, oops, I have a typo. Oh, it's this. All right, so now I'm going to go ahead and run it again. All right, and there you go. So this is what I was talking about. So with singular value decomposition, you can go from, each sentence represented as a feature vector of size 15. Let's say we're using a vocabulary of 15 words. Or each sentence represented as a vector of just 2. features, where these two features are a linear combination of the 10 original features, right? So based on the, the singular value decomposition technique, we don't really want to get into the specifics of the math or the theory of it, just really to know as a data science practitioner that you can do this, right? You can go from this to this, and the advantage of this is that now, well, it's obvious here, whereas the matrix here is 7 by 15, now our matrix is 7 by 2, right? So it's a smaller matrix in size, and so that's a huge advantage. So this is good, if, as I said before, let's say you had, 1 million records or 100,000 records by 10,000 columns, right? So imagine if you can compress that to 100,000 records by 3 columns. And really, the technique is so good that you do lose some information, but it's only like 15%. So it's still, out of the original 100% information you had, now you still have 85%. And so that tells you that that may be enough for your machine learning. And that's going to save you, time and money and resources in memory and in everything else. So it's certainly a good technique to know about. There's more to singular value decomposition than this, but I really, I was just planning on covering this for now to kind of give you an example of unsupervised techniques. So notice that in this technique, we never had to use labels, right? This has nothing to do with labels. This is just the feature vectors themselves. So this is basically the X matrix, not the Y matrix. And this is still just the X matrix, but a little bit more compressed. Okay? Now, the advantage of this is that you can, whereas before you could not plot this, so you were not able to plot this matrix, now that the matrix is compressed, you can plot it. All right, so that's the next thing that I'm going to do. So I'm going to create a little plot of this. So let me go back to the code. And so now we're going to use matplotlib to visualize this. And this is where clustering kind of comes in, right? Because the idea would be, wouldn't it be nice if we could cluster these 7 sentences into nice little groups? All right, so let's go ahead and try to do that. So we're going to now, plot the matrix. Let's say, oops. So to plot this matrix, we are going to need to extract the data. So I'm going to do, I need, because there's 2 features, right? So I can just use a 2D plane, Cartesian plane. So I'm going to have x, s, and y, s, or just x and y. So I'm going to say x and y. I could also say x1 actually and x2. So let me do that. All right, and now I'm going to use a list comprehension in Python, basically. So I'm going to do for w in compressed DTM, right? So remember, this is a matrix of 2 columns, right? So right now I'm reading every row, and I need to grab just one of the columns in each row. So what I'm going to do is I'm going to say W0, and that gives me the first column. All right? And so I save all of that in X1. Then I do the same for X2. So I'm going to say, create the list comprehension again for W in compressed. So for W in compressed DTM, so underscore, compressed DTM. So now I'm going to take out the W1, right? So one, every iteration I grab either column 1 or column 2. Once I have that, I could, then I can just plot it basically. So I'm going to do import matplot matplotlib.pyplot as plt. All right. Then I'm going to create a figure using the plot figure module or function. So I'm going to say plot figure. And then I'm going to create a scatter plot. So I'm going to do plot scatter of x1 comma x2. All right, and then finally, just some labels. So I'm going to do plot x label will be basically f1, and then plot dot y label will be f2. All right, and once I have that, I can just go ahead, maybe give it a title. So I'm just going to say plot dot title, and I'm going to call it compressed data. All right, so compressed data. And finally, we should be ready to print, so I'm just going to do plot.show, and this should create a graph of this. So I'm going to run the code. Control X, Y. All right, and there it is. So I've created the little graph here, and this graph then is plotting all my sentences. Or this could be malware, right? So if you imagine, if we go back to the malware lab, right, then we have a way of plotting our malware. Maybe if you can, each one of these points is in a Cartesian plane of f1 and f2, right? And it represents one of those sentences, like, cybersecurity is fun, soccer is nice to watch soccer, etc. So each one of them is a sentence. But if we go back to the malware lab, these could be goodware, this is one goodware, and this is another example of malware, etc. So the advantage of this is that now these points, graphically, we can see that there's basically 3 clusters, right? So we can see that this is kind of a cluster, and this seems to be a cluster, and that seems to be a cluster. So that's what unsupervised learning is about. It's about discovering these clusters that we see here. If we just wanted 2 clusters, then it would probably select this as a cluster and that as a cluster. If we say 3, it'll probably select this, that, and that. And so really that's how it works, right? That's really what unsupervised learning is about. So now we would need to apply the k-means algorithm to discover some clusters, basically. So let me do that. So I can close the graph now. All right, and we're going to go back to the code. All right, so I'm going to scroll down here. So I've plotted the information, and now maybe I want to do something else. So let's see. All right, so I already imported the k-means cluster. All right, so I'm going to create, so this is going to be k-means, and I need to create the k-means object. So k-means, I'm going to say that I want 2 clusters. So, oops. So k-means parentheses. So I want 2 clusters, and then I'm going to say that the initialization should be random. So that basically means that, the k-means cluster, how it works is that it picks 2 starting points on the graph, right? And it picks them at random, and then from there it starts looking for the clusters until it finds them. So in this case, I'm just going to say that that initialization should be random, although you could pick specific points as well. All right, so I'm going to say random, right? I'm going to initial, for the random, you want to provide some value, like try 10 different random numbers when you're doing this cluster. So like 10 iterations basically, and until you figure out, something that seems optimal in the algorithm, right? So I'm just going to say initialize n init. I'm going to set it to 10. All right. And then I'm going to say that the algorithm should run for a maximum iterations. This is a small data set, so it doesn't need that many iterations. So remember, this is an algorithm that's optimizing. It needs to have a random state to initialize. It needs to have how many times it should try things randomly, and it also needs to have how many times it should run until it sees if it's found an optimal solution. So here I'm going to say max iteration equal 300. So for this data set, that should be enough. All right, and then I'm going to say random state equals 0. All right, so that's going to be the seed for the randomization. All right, let's try that. Let me run the code. Let's just see if all parameters are there. All right, so everything looks good. So now that I have the k-means object, I'm going to apply it. So now I'm going to create a set of. So what this is going to do is it's going to take every sample and it's going to tell you if it belongs to one cluster or the other cluster. All right, so I'm going to do y k-means. So y k-means. All right, this is going to be the output, so I'm going to apply k-means. And actually, I just realized this name looks, so I'm going to say k-means 1, so it's not confused with the library name. All right, so k-means 1 dot fit predict. All right, and I'm going to apply it to my DTM compressed DTM, right? So if I'm going to apply it to the original one here, right, and I'm going to try to cluster those points now. So I'm going to do compressed DTM, okay? Since that word is really, so that produces y k-means. All right, so now I'm going to go ahead and start plotting this. So I have to do a little bit of plotting magic here to print out this data. So I'm going to say, so the algorithm did its job. So if you don't want to plot it, you just want to use the results. What you can do, and so actually let's do that. We're going to plot it, but first let's just print out what's in. So print out y k-means. All right, so we're going to print out y k-means. So I'm going to do Control X, y. All right. And there you go. Right, so this little vector is actually the result because there's 1, 2, 3, 4, 5, 6, 7 entries here. That corresponds to the 7 sentences that we had initially, right? Basically these 7 sentences. And now we've just clustered our data, right? So most of it was clustered as 1 and 2 of them were clustered as 2. So it made the decision on its own to do this. So now, however, it's hard to interpret like this, so we really want to plot it and see what it looks like. So let's go ahead and do that. So again, I'm going to create, so I'm going to call plot dot scatter. So plot dot scatter. I'm going to take the original data in compressed DTM, and now I'm going to have to do a slicing again. So I'm going to have to slice some things. So I'm just going to say, so compressed, if you remember, compressed data is all the sentences as vectors of two features, right? So I'm going to say I need the x and the y for these, so it might actually be better. So to make this a little bit more obvious, let me do this. So I'm just going to do this a little bit differently. So I'm going to say x1, y1, right? So that's what we want to print. But we're going to do a little bit of slicing magic here. So I'm going to take compressed DTM. And now I'm going to say, okay, I'm going to use yk-means. Yk-means. If the value in yk-means is 0, all right, so I think the best way to understand this, since we're doing slicing here, is actually to create, I was going to do it like in a more shorthand version, but I think it's difficult to interpret it, so I'm going to take a more longer, I'm going to provide a little bit more code, but it's a little bit clearer what I'm doing. So what I need is really, I need the indices cluster 1, and I need the indices cluster 2. Right? So I need to extract those indices first so that I can slice. Remember that when you have slicing, what you do is, let's say you have x, and you have something like this, so then you do something like from 2 to 6, comma, and then like 4 or something like that, right? So that's really what we're doing here. So I need the indices that I'm going to select. So remember that compressed DTM has 7 sentences where each one, or 7 entries for each sentence, where each one of those entries has 2 features, 2 values. So I need to get the values from compressed DTM for both 0 and 1. For feature 0 and feature 1. So I definitely need to get that. Oops, what happened here? All right. But then I need to know which indices. So once I'm going to do 2 scatter plots, one of one color and one of another color. So this will be the cluster of only the values for, let's say, cluster 1. So I need those indices. So to get those indices, I'm going to say I need to grab yk-means, or yk-means, which is this one over here, right? So yk-means, I need to grab this one, and I need to slice out the indices for class, or actually the name of the clusters, let me change that to 0 and 1. 0 and 1. So I need the ones for 0. So I'm going to do k-means equal 0, right? So that, with this approach, I will be able to take all the indices that match 0. Then over here, I'm going to do, again, y-means equal 1, right? So this is going to be, yk-means. So that's going to be all the indices that match. I'm going to get all the indices of values that are 1 in y-means. So now that I have those indices, then I can plug them in here. So I'm just going to say indices C0, and here I'm going to do indices C1. All right, so that, I think that should be pretty clear. So now I'm grabbing the indices that belong to cluster 0 from compressed DTM, and I'm grabbing column 0. Then over here I grab column 1 for all the indices. Oh, this should be C0 actually. It's the same. C0. They're both C0. So really what I want is, yeah, so actually to even more clear, let me delete this. I'll type it up below when I do that second cluster. All right, so maybe I'll add a little bit more here, like this is cluster 1, or cluster 0, sorry, it's cluster 0, all right. So I extract from Y means the indices of the values that are 0, I save them in indices C0, then from compressed DTM, I need to grab columns 0 and 1 for only those indices that belong to cluster 0. So that's what I have in X1 and Y1. So now that I have these, I can just add these here. So I'm going to say X1 comma Y1. All right, then I'm going to, these parameters just have to do with like the color of the cluster, etc. So I'm going to say the size is 50, and then the color should be, you know, light green. So I'm going to do light green. And then the marker is a star. And then we're going to label this as cluster 1. So label this as cluster 1. All right, so cluster 1, and that's it. So that's the first cluster. Then all we have to do now is repeat this process. So I'm going to do, you know, cluster 1 here, or actually to be more consistent, let's call this one cluster 0. All right. So now cluster 1. Okay, I'm going to repeat the exact same process. I need indices for cluster 1 now, which will be y underscore means, but in this case it's going to be equal 1. So equal 1. Right, once I have that, then I can do, again, x1, y1. So now I'm going to say compressed DTM, and I'm going to select indices for C1, and I still need columns 0 and 1, so this is 0. This is going to be compressed DTM indices C1. So this is the values in the cluster 2, and this is column 1. All right, and once I have this, pretty much the same with the plot. I'm going to say plot dot scatter x1 comma y1, and now the symbol is going to be, the size is the same, about 50. Now it's orange instead of, you know, a different color, so orange. The marker, a circle. Marker, it's like an O. Okay, and then I'm going to label this as cluster 1. All right, so that should be it. So now let's go ahead and try to plot this. So I'm going to do plot dot legend plot.legend plot.grid and finally plot.show. All right, so hopefully this will show us how the k-means clustering algorithm takes the data and now finds these two clusters. So I'm going to do Control X. All right, I'm going to run the code. This is the original data. Notice how it looks here. Okay, I got an error, so okay. Let me see. Let me try this. Let's try this again. Oh, I have another typo. So this should be YK means. All right, and there it is. So this is the, so it's working this time. So let me run it one more time. So I'm going to do Python. So I'm just going to bring both graphs into the picture. So there's one. And you can see it here, right? So this is the, you know, the points, the three, and 1 here. So if I now, let me save it on the desktop. Okay, so that's going to be figure 1. All right, and then here's the other one, so I'm just going to save it on the desktop as 1. All right, so I have both of them. Code ran. So let me now open both. Okay. And there you can see there's one. And here's the other one. And you can see, so this was the original one with the 3 points. You can see the 3 points here, this point here, those 2 points here, and a point at the top. Excuse me. So we built that, we used an algorithm that had, we wanted 2 clusters. So basically it created that cluster and that cluster, right? So it basically grouped this, and we could intuitively look at this and draw. If we're only creating 2 clusters, I had originally said that I was going to do this and then this. And it kind of came out like that, except that this 1 point was added to this other group. All right, so that's basically it. That's our k-means algorithm. So we went from the original data like this to data that looks like this. We discovered 2 clusters, one in orange and one in green. All right, so I will just quickly summarize the code. So basically, you know, we created, here's the unsupervised learning code. We used a k-means clustering algorithm. Remember, this is unsupervised learning. We had no labels. We had libraries. This was our data, 7 sentences. We used the bag of words approach that we had discussed previously. We used singular value decomposition to kind of just compressed the data. So if we had 15 features, we compressed it to just 2 features. So it's, the vectors, that way we could plot the vectors basically. Now keep in mind, I should say that you can apply k-means to feature vectors of more than 2 features, right? So you can have feature vectors of 15, 20, etc., and you can still apply k-means. You will not be able to plot it, obviously, because we can't plot things of more than 3 dimensions, right? So 4 dimensions, 5 dimensions. But the k-means algorithm still works. And so if you remember, we were still able to get the results when we printed this, right? So when we printed this one line. So for bigger vector spaces, you will only be able to get, for your answer when you apply k-means, you will only be able to get this, and you won't be able to plot. But for our purposes, because we were using a small data set, and for illustration, we've used 2 dimensions. So anyway, so as I was saying, the vectorizer provides the bag of words approach, then singular value decomposition compresses the data from, let's say, 15 features to 2 features. We printed the data here, and then we plotted the data without applying k-means clustering. Then we called in the sklearn k-means clustering algorithm. We decided that we wanted 2 clusters. We fitted the data. It gave us k-means, which is the answer basically. And then finally we decided to do a little bit of plotting just to kind of visualize the results, right? And that's what we did. So and you can see that then here in our 2 graphs, as I said, right, we have our 2 graphs, the original graph, and then the cluster, the graph with the 2 clusters. All right, so that concludes our unsupervised learning discussion and video using sklearn.